You recall that during the last lecture, we talked about a guideline called the Liskov Substitution principle. Can anyone remind me, in very simple terms, I'm just looking for a very rough communication of it. What does the Liskov Substitution principle say? Yep.
Subclasses must be subtypes.
Okay. So all subclasses must be not merely pro forma subtypes, just kind of by appearances, they're just automatically considered as subtypes. They need to be legitimate behavioral subtypes. And this is really trying to make a distinction between something where you say, well, A is going to be a subclass of B, and the compiler then will, as long as you observe certain very basic things having to do with the signatures involved, method signatures, it will allow you to pass around an A as if it's a B, right? So you could say, my class is a subclass of this other one, or it implements collection, so it implements this interface, and it will let you pass it around as if it's a collection, collection object. But that's getting a free pass for a lot of what it really means to be a legitimate subtype. And Liskov substitution principle is about the burden, the responsibility, the onus that's on us as software developers to create legitimate subtypes that are behavioral subtypes of a supertype. And what principle does it lay down? What rule does it lay down as the fundamental guiding principle for that? Yes. Thank you. Any property that you can prove about a supertype, you need to maintain for your subtype. If someone is going to look at the definition of the collection interface or the queue interface or any of these other interfaces that are shown here, a set or a list, they're going to come away with some impressions about what's guaranteed by that. They're going to look at the methods and say, I wonder what's possible here. For example, does it handle null values passed into it, a certain method, or does it ever yield a set which is empty, or what have you? You're going to look at these things, and you're going to come away with certain impressions about what's possible and what's not, what's guaranteed and what's not. And those impressions could be at the method level. You're going to come away with this impression, this method called, find max, or max, that it always returns a non-null value. Right? You might read the specification and say, okay, it always returns a non-null value. So that might be a property that's about a particular method in isolation. Or there might be properties which are more about how collections of methods jointly behave. They jointly behave in such a way that certain properties are guaranteed. And we saw a few of those properties in some examples last time that I threw up in the final minutes of class. Can you comment on what are a property? It's not just about one method in isolation, but it's about something that results from the cooperation of methods. Give me a property that might be maintained.
The arguments have to be equally restrictive or more restrictive than the arguments in the superclass.
Okay. They need to be able to actually take, for the arguments, less restrictive. For the return values, they can be more restrictive. You need to, for the subtype, to not allow for any surprises, right? If someone's going to call it thinking that it's an instance of the supertype, the apparent type, that's all they know, it's collection. And if they expect, oh, but collection takes these arguments of these sorts, then if it's secretly one of your class, an instance of your class, it's got to be able to accept those arguments. But it might accept a broader set, right? It might accept a broader set. But you're exactly right, Jonas, that for things like the return values, the subtype can return a more specialized set because those could be returned by the supertype. Okay, but I'm trying to talk here about, so there's certain properties about particular methods, about their arguments, and about their what the values they return, things like the precision of a square root operator that I referred to last time, or even the types that it takes in its arguments, the types that it returns. There's certain properties about them. But those are properties about methods in isolation. There's some properties that transcend any one method. They're more emergent properties that hold for the class as a whole. Given the methods that are available for the supertype, there might be things that are guaranteed. Give me an example of one of them. If this is a counter, we might say, well, based on these methods, the value of this counter is always positive or non-negative. That would be an invariant. Hey, it's guaranteed to be non-negative. Whatever value it is, it's guaranteed to be non-negative. It's a guaranteed property. And it's not about one method in isolation. It's that the constructor maybe initializes it to 0, and then you can only increment it. And so you reason about those two things together, and you say, well, it can never go negative, right? It's not about one method. It's not that there's one method that guarantees that property of positivity. It's the combination of how the constructor works and how this other method is the only one available. Okay, so one thing might be it's non-negative, great, or positive, or what have you. That's an example of a property, that it's even, right? That you can never have a string that's empty. That has 0 length. Those can be properties that are invariants about the class. But then there's another set of properties that are history properties. They're not about the class at any one point in time, instance of the class at any one point in time in its properties. They're about, if you compare 2 points in time, class, time A, time B, an instance of class time A, time B, some property that maintains between those 2 times. Give me an example of a property for a counter that is a history property. Yes, it never goes down. It only can stay the same or increase. So if we look at it time A and look at it a little bit later, time B, it can never be going down. Okay, these seem like weird things to mention as properties. But the point is, ladies and gentlemen, that someone could be counting on them. Someone who thinks they're using just an instance of the superclass, or they're looking at the interface, the definition for collection, or the specification for set, or for sorted set, or for map. They may be looking at this, and they may be saying, oh, that map can never be empty. Or this value, the value that's returned by a list is never null, or what have you. And then their code could count on that. They know they don't have to check for null. Or if it's something about not declining, they know that if they check it, that later in the code, they don't have to worry about that value having gone down. That it's always going to be writing to successive values of an array in increasing order. It's never going to overwrite earlier values. That could be something someone's counting on, right? They look at the specification, they could count on it. And ladies and gentlemen, the Liskov substitution principle says that we need to be able to, if we create a subtype, and we're going to pass it around as if it's a collection, as if it's a map, as if it's a queue, as if it's a set. In other words, if we create a subtype of one of these, and we pass it around, and we masquerade it as if it's one of these, we sure as better be able to guarantee things that someone might be counting on reasonably based on that supertype definition. based on reading the specifications, say, in the Java standard libraries, and if they can be counting on something very reasonably from that, we need to hold true to it, or else we can break their code. Their code was written perhaps long before our class was ever written, long before it was conceived. Their code is written against collections, and their code has worked for years and years and years. And suddenly we give them a collection that doesn't stay true to, isn't consistent with the behavior of the supertype, of what's guaranteed by a collection. Suddenly their code breaks. We've injected this new class, and we've screwed over their code because we're not adhering to things that they can reasonably count on. We're not adhering. We're FredX, and we're not allowing that package to come in by 12 noon and be delivered by the guaranteed time. We say, we're different. Well, guess what? That doesn't cut it in the business world, and it doesn't cut it in the software engineering world. It's a recipe for real problems. It's a recipe for bugs. It's a recipe for crashes. It's a recipe for poor quality code. Okay? So Liskov substitution principle basically says, look, if you can prove something reasonably from looking at the supertype, if someone could be counting on that property, maybe it's a history property, it never declines. Maybe it's invariant, it's always greater than or equal to 0. Maybe it's something about the types taken in, what have you. Maybe it's something about the methods, the values that this particular call process has to be able to handle. Then we need to guarantee it for the subtype. If we have a supertype which has a square root operator and it guarantees that the values returned lie within 10 to the minus fifth of the actual value, we got to adhere to it. Now we may do better. It's not a straitjacket. We can't do better. That we have to just mindlessly adhere to the dictates, exact same dictates. We can do better. We can return something that's accurate within 10 to the minus 8, but we cannot return something that's not legitimate given that supertype. Something only accurate within 0.1. Does that make sense? Okay. Okay. So recap. That was a recap. Let's just reflect on the fact that we can decompose the considerations here into three pieces. One is method signature compatibility. And this one is particularly easy to guarantee because the compiler checks it. The compiler checks whether the methods are compatible. So it will check things like this. And it will flag things that are off base and allow things that are okay. And this varies by language. Since Java SE 5.0, I think, allows contravariant return types. In other words, return type that vary from the supertype. But it doesn't, it requires the actual types taken in by a method to be the same. That's different for different languages. Okay? But generally the compiler will tell you if you are off base with this. Okay? So this one is, I'm telling you about this, it's part of the package, and if you're fighting with the compiler sometime, maybe this will help you understand why. But the other two are more tricky because those are things you folks have to check. Those are things it's incumbent upon us as software engineers to check. Okay? And those things are the methods of the subtypes must behave compatibly, consistently, must hold true to the behavior of those of the supertype. So I get the example of square root, right? It's an example. That's about a method in isolation. And then there are these properties, things like history properties and invariants that have to be held true. Okay? Does this make sense? Okay. And you understand why this is. This is not merely being picky. It's not merely being, being pristine in our calculations. This is about breaking code, folks. It's about breaking other people's code. It's about screwing other people over because they are legitimately counting on certain things being true, and you can't just come in willy-nilly and do whatever you want. This is about, if you're claiming to implement an interface, it's not merely filling in the blanks of those methods with the exact same signature and thinking everything is fine. It's about when you look to implement a given method, you need to ask, is my implementation going to be consistent with the behavior that's guaranteed for that method? Does that make sense? Because if it's not, and someone's counting on the properties of the supertype, and you pass one of yours in, if you don't guarantee those things, it'll break that. It can break that code very easily. Okay, and this has happened many times, and it leads to bugs that are hard to debug and a real pain in the butt. And you can head it off pretty easily. Okay. So we talked about some examples last time, and we went through these last time. I have lots of others, so I won't go through them again. I will just note that I map out which are legit and which are not. Here we have the face type with this counter. The second one, where we have counter 2, makes it contain 0. But we have this thing called increment, which we're filling in. You might think, oh, this implements increment up here. This is the interface, and we're implementing this in our own way, and we're all fine. Well, it's not fine, folks, because our implementation of it does not adhere to the guarantees up here. Instead of incrementing it by 1, which is kind of implied by the word increment, it doubles it. That just doesn't cut it. It's like claiming we're implementing a square root operator that really computes the cube root, or computes the value divided by 2. That's a fraud. That's fraud X, right? Okay, here's one that's perfectly fine. Here's a subtype. It adds another method, double value, that doubles the value, contains twice the value, but it doesn't override increment, or it doesn't change the implementation of increment, and by implication, it implements increment to actually increment, and that's fine. I mean, if we want to require this as a subtype, for this, we have a promise that we provide a double value. That's perfectly consistent with this thing here. Are people comfortable with that? Why that's consistent? We can get a double value. This will yield values that could have been obtained by increment if someone just thinks they have a regular counter. They don't know about our class because they wrote their code long before our class existed. All they know is one of these. Any value you can get through this, any value you can get through this subtype here, you could get through this. Doubling 0 gives 0. You can get 0 through this by just initializing it. Doubling 1 gets 2. You could have gotten 2 by incrementing by 1. So someone won't be shocked to see an even value produced by this because they could have gotten it through that. Does that make sense? Okay. This one I said is bad. Why is it bad? Why could it cause problems? It could lead to a negative value. Great. Excellent. Excellent. So this could lead to negative values, and someone could say, well, someone could be staring for hours at this counter. I mean, look at this. I have this counter. And there's just no way you can get a negative value. Suddenly I've gotten a negative value for a counter. I mean, this isn't a legitimate counter. It's a fraudulent counter. And here, decrement positive, well, it maintains the invariant. It's greater than or equal to 0. What's the problem? Problem is that it is declining over time. And we could be counting. You might think this is weird, but someone, if they have this counter up here, they could be filling in successive values of arrays, and they're counting the fact that it's always the same or increasing. So we never overwrite earlier values in the array, right? Someone could be filling that in. It's possible. And suddenly they're getting back values which are going back to earlier values. They're getting in this thing that looks like a counter. It's masquerading as a counter. It appears to be a counter. Someone passed it into it from elsewhere in the system, from your code somewhere, maybe. And suddenly it's doing things which seem impossible given this, and which breaks their code. Bad news. Okay. Okay. Let's talk about this. Here's another one. Okay. So here's the same one. Here's the super type. Here's my counter 2. My counter 2 has a reset operator. It can reset it to an arbitrary value less than or greater than or equal to 0. Is this a legitimate subtype? Are the promises made by this type down here at the bottom, are they consistent with, do they adhere to all the guarantees made up here? That someone could come away with a strong, are there certain properties someone could come away with a strong impression about here? Think that are basically guaranteed if you have this set of things, which will be violated here.
Always increasing.
Yeah, the always increasing. So this one can decrease, so doesn't cut it. Okay, how about this? Here's a dual counter. Dual counter, it maintains the normal counter, but it also has an extra counter with it. So it has get for the normal counter, but it has a second counter also, and a second increment for that other counter that corresponds to kind of the increment here. Maybe I should, to make it consistent in its notation, I should say increment. Increment 2, it should be. Increment 2. So we have all the methods that, well, I'll have the increment in there as well. It just, we have increment 1 and we have increment 2. I don't want you to get distracted by that. So we have increment 1, we have increment 2. So is this guy a legitimate subtype? Could someone be rudely surprised by this? This one on the left here? If they think it's just a counter? If they're treating it like a counter, they think it's just a counter, they inspect it, maybe it was created elsewhere as a dual counter, but it was passed into them as if it's a counter, and they're looking at it as a counter. Could they be rudely surprised by this? If all they see are the things that they're treating as a counter, so all they know about is get and increment, could they be rudely surprised? No, it's perfectly legit. Perfectly legit. We've extended it in a perfectly consistent way. How about this thing on the right? Swappable dual counter. Now it's the same thing as the dual counter, but we can swap the two counter values. Okay or not? No. No. Why is it not okay?
The same thing as with like the reset and stuff.
Yeah, you reset it.
Might be lower.
If you go down. Yeah. Good. Okay, how about this? You folks may have heard the old chestnut. You know, a rectangle is a shape. A square is a rectangle. And that's often used in basic courses in object-oriented programming to guide creating of subtypes and subclasses. So here we have a proposal to have rectangle as a subtype of shape and square as a subtype of rectangle. And what I want to note here is this very specific thing that we, in this particular implementation, we have a set sides operator, which sets the values of the sides here. And rectangle implements it, and rectangle has it, and square does as well. Is this a legitimate subtype of that? Why not?
Because its arguments are more restrictive, assuming it means the sides have to be the same.
Exactly. This guy will bomb out. If this is a square, we'd expect it reasonably. If you said, well, set side 1 to be twice the value of side 2, we really reasonably expected to have an assertion failure or an object in some way, because that's not consistent with it being a square, right? So square is actually not a legitimate behavioral subtype of rectangle. Now, I would note, so the answer is no because of set size. Now, I would note, however, that if square was immutable, all you did is you created it by specifying the value of, the side, and that was specified in the constructor, and it stayed with that side after that, and you had get sides, get side 1, get side 2, or get sides, returns an array of things for the sides. And if rectangle had a constructor that took two values of each of the sides, that would be a perfectly legitimate subtype. It's because you can't have the set, and it can't be set to two different values. This guy is going to accept a more restricted set of legitimate values than this one. The promises made here, implicitly or explicitly, I mean, you don't see any explicit specification here, but logically, this guy is just going to throw out certain values that are accepted here. So it's not a legitimate behavioral subtype. Does that make sense? Okay. Yes, question?
How about reverse, like the square is the subtype of the rectangle?
Okay. Square is the subtype. Square here claims to be a subtype of rectangle. I would say by the Liskov substitution principle, it's not a legitimate behavioral subtype as it's declared here. Now, I could create, again, a different definition here where, let's just do it. So here we have class shape, right? And we have draw on here. I'm just trying to be true to this. Class shape, and we have draw as the method, and then we could have class rectangle, right? Now the key thing is I'm going to make this immutable, and this will have rectangle, and it takes a double side one. Really have a better name than that, but double side 2, and then it has a draw. And okay, so these are the sort of methods associated with that. That's fine. And then we could have a square here, square, and all this takes in is a single thing here. And I'm going to actually spice it up a little bit. I'm going to have a method that returns double side 1 and double side 2. Okay, there we go. And side 1, side 2. Alas. There we go. Yeah. Okay, and then we're gonna have back here. Okay, and then we're gonna have this. Would square here be a legitimate subtype of rectangle? Yeah, no problem. No problem. No problem at all. We could have this as a so this would be it extends rectangle, for example, extends rectangle. Yeah, sure. And rectangle extends shape. Shape. The promises here made, no problem. Perfectly consistent with promises above. We can ask for double side 1, double side 2. It returns values that are more restrictive there, but that's okay. Returning values more restrictive than the supertype is okay. Throwing away values that are legitimate for the supertype as arguments for the subtype throwing away values that would have been legitimate as arguments for the supertype does not cut it. Does that make sense? People are comfortable with that? Okay. So this is okay. This is okay. That wasn't the most expressive title, but we'll come back to that. Okay, here's another example. So here we have an inset. Okay. Consider bag set. It's identical. So the idea is we want to create a subclass bag set, event set. It's identical except that it allows for and it maintains information on multiple inserts of identical integers. So inset just excuse me, I should really call this to be a better name here. I should call this int bag. Okay. And then we'll call it int bag. Okay. So here's int bag. We want an int bag that's a subclass of this guy. I've never seen slides composed like that in front of you, right? Okay, int bag is a subclass of int set. and it basically inherits all these methods. So it claims to adhere to all these methods here, except that it differs in that if you insert a given thing more than once, let's say you insert the value 2 more than once, it'll keep track of that. So if you insert it and then if you insert 2 twice, then you remove it once, and you ask, is it in there? It'll say yes, for bag set. Actually maintains count of them that have been inserted. And if you remove them, it'll decrement the count. If you add them, it'll increment the count. So the idea is, we want to reuse all this good stuff over here on the right, and we just want to tweak it in a certain way to have this extra property. So here's the question. Is this a legitimate subtype? Could we be rudely surprised if we think it's merely an int set, and we're manipulated as if it's an int set in code that was written long before bag set ever existed? Could we be rudely surprised by being given this thing that's actually a bag set, and excuse me, actually an int bag, excuse me. It's actually an int bag. Could we be rudely surprised if we're given something that's secretly an instance of int bag? Maybe because our code somewhere else is using this library that was written long before our code. We give it an int bag. Could that code be rudely surprised? How could it be rudely surprised?
Like if it doesn't answer to something,
Yeah.
and it counts on like an exception or some kind of error code, it won't get it.
Yeah, so it's not really specified exactly what happens here, but the overall concept here, I believe, was meant that if you insert it twice for an int set, it just treats it, well, it's already there, it's already there, and if you were to then remove it, it'll be gone. So insert it twice, remove it once in an int set, it's gone. It's not part of the set anymore. You add it once, it's part of the set. You add it twice, well, it's still part of the set. The set's no different. Add it 3 times, set's no different. Remove it, it's gone from the set, right? Whereas with an int bag, you add it thrice, you add it 3 times. Once, there. Twice, it's there, but it knows it's there twice. 3 times, it knows it's there 3 times. And now you call remove. Is it still there? Yeah, it's still there. It knows it's there twice, moreover. And so someone could be counting on this property that if you insert it more than once, it doesn't really matter. In their algorithm, they know, oh, well, if we've seen the city before when we're routing, doing some routing of trucks or whatever, it's just already in the set, and so it doesn't matter if we insert it again. Later we can go remove the city, and it'll be gone from the set. They could be counting on that property in some algorithm. You may think that's kind of unlikely, but algorithms can be quite complex, and you could be counting on this property. Sometimes you have to reason very carefully about how this behaves to come up with your algorithm. So someone could be counting on that, and guess what, folks? Suddenly our int bag does not adhere to this. Suddenly our int bag is saying, it's still there, after we call remove. And the person could be unhappy. It could break the algorithm. Can you understand that? Can you imagine the case? Okay. Okay, so there's the case. Okay, here's more cases. Why am I giving you all these cases? Well, for one thing, I consider this it's a little bit fun. But there's another reason. It's because I'm going to be testing you on this. I'm going to be testing you on this significantly in the final exam. Better now than then. Right? Better while we're doing it together and you can ask questions. Okay, so here's course timer. And there's a find timer. Okay, so we have a course timer, and find timer extends course timer. Is it a behavioral subtype of course timer? Course timer, you call its constructor, begins a timer that's actually timing I mean, how long it's been since it was instantiated, since it was created as an instance. And you could call its method minutes and get the number of minutes there. Okay? Make sense? You can create an instance of it, call minutes, and you'll get the number of minutes that is on there. But suppose someone came along some fine day and they wanted to create a fine timer. And they want to support all this functionality of course timer, but they want to return the number of seconds, not just the number of minutes, but the number of seconds. Would that be a legitimate behavioral subtype? Yeah, sure, it's perfectly fine. Yeah, sure. Gives extra information. It adheres to all the methods up here. No one would be rudely surprised if they get something that's a fine timer because someone passes it to them from some new code that's written. Maybe we wrote it in this library. It's written long before in code. It deals only with course timers. They're not going to be rudely surprised. They won't even know about the seconds method, right? We're treating it and calling in minutes, and they won't get anything odd. If they know it's a fine timer, they can call seconds, great. But if they don't, it's behaving perfectly consistently. They're not going to be rudely surprised, right? Yeah, perfectly good. Perfectly good. A fine subtype. Perfectly legitimate behavioral subtype. Okay, how about modulo timer? Modulo timer is like course timer, but here we provide a method minutes that returns the number of minutes rounded down to lapse in the final hour of time since the constructor was called. So this always goes between 0 and 59. It sort of, basically it ignores the hours. So if it was created 2 hours and 40 minutes ago, it will return 40 when you call minutes. Okay? Is that a legitimate subtype of course timer? If you pass one of these modulo timers in as if it's a course timer, could you be rudely surprised? Give me an instance where you can be rudely surprised. What could happen? Like,
suppose I want to get the course minutes maybe larger than 1 hour, so
yeah,
it's probably like 1200 minutes, but it's just returning maybe 15 minutes.
Yeah, exactly. Okay, so you're expecting it's going to return, 2 hours and 40 minutes. In other words, 160 minutes, and it returns 40 minutes. You're going to say, what? Is the clock on this computer off? I mean, was memory corrupted? Was something wrong? No, it's a fraudulent subtype. This is a fraudulent subtype, ladies and gentlemen. This is the equivalent of fraudulent FredX modulo timer. All right? Do people understand that? Someone can be shocked legitimately by the behavior of this passing as if it's one of these. Doesn't cut it. It's not consistent with. Okay? Okay, how about pausable timer? This one has all the stuff of course timer, but it allows you to pause it. It allows you to resume it. Okay, Josh is shaking his head. Why not? He's correct.
Because it changes the value that is expected.
Okay. Yeah. So someone let me play a devil's advocate position on this. Okay, you're correct. Let me play a devil's advocate. Someone could be recently say, what? Let's see. Okay, so you pass in a pausable. So I'm some code that was written with respect to course timer. It was written knowing only about course timers in the world. And I've secretly gotten a pausable timer. Well, how is that going to cause a problem? After all, I don't even know about these other methods like pause and resume. So how is it going to cause, how am I going to note some weird behavior with this? I mean, I don't even know about this method. I'm not going to call them. Yes, Josh?
No.
Oh, okay. So why is that not an effective argument?
Because if you have a timer that's dealing with stuff like ours, it could easily be modified elsewhere.
Yes, exactly. So somewhere, okay, maybe I don't know, in this old code, maybe I don't know about pausable timer, but someone created that as a pausable timer. Somewhere else may know that it's a pausable timer. And they may be off in their area of the code calling pause on it, calling resume on it. And meanwhile, I'm counting on this thing. All I know is that it's a course timer. That means it's being passed back to my code as if it's a course timer. All I think is the course timer. So I think it's keeping track of the legitimate time elapsed since it was created. But it's actually being called pause and resume willy-nilly off there. And so suddenly I've been counting on properties of this thing which aren't guaranteed. Somewhere else in the code knows all about these other methods. And they can call these things and it could lead to rude surprises for me. Like after 3 hours of operation, it still only increments 1 minute. I can be rudely surprised, right? It's the reasoning for a lot of these. Somewhere else in the code, they know about these other methods, even though my code doesn't. And that could lead me to see something I think is impossible. Yes, Joe.
I just have a little tangent, little idea with this. Is if there was a second integer being keeping track of that was just incrementing whenever it's paused.
Yep.
And if there was a second method to get that value that subtracted the total time from the pause time.
Yep.
And essentially added the functionality of adding pause, but still keeping the full functionality from the original. Is that valid?
Okay, so yes, with a proviso. Okay, so the question was, suppose you had a timer, kind of like pausable timer, but it had a way of maintaining the true full time, but it also had a way of sort of maintaining the time taking into account pauses, right?
Yeah, the unpaused time.
Yeah, the unpaused time as well as the paused time. That could be legitimate as long as, folks, minutes always return the time not considering pauses. Maybe you have minutes considering ignoring pauses or something like that as a method. And that returns the time that does not count the time when it's paused. You see, you couldn't override minutes.
Yeah.
So it was returning it was ignoring pause time, because that would lead to the real sort of objection that, wait a minute, I'm counting on this property of minutes that it's really the full time. But you could add another method that's like minutes ignoring pauses or something, or in other words, minutes not counting the time when it was paused or something like that.
If there was minutes and unpaused minutes, like
right.
Minutes was the total and unpaused
That's
minutes
right.
was...
That'd be fine.
Yeah.
That'd be fine. And so it adds this, and it doesn't interfere with it in any other way. Someone else in the code could be using the other functionality of it. Great. But the key is that the code that's counting on this functionality not be broken, because it, not be counting on...
Just
yeah.
Because the functionality, you can code it into there as long as you're not screwing with
That's right.
the assumptions that are from the...
That's right. That's right.
So,
Yeah, you can add all sorts of functionalities as long as you're not screwing up the assumptions, screwing up what people, and undercutting, yanking the rug out from under them in terms of what they're counting on. Right? The things on which they are counting. Okay, how about resettable timer? Is that a legitimate subtype of course timer? No. It's the whole thing. First of all, it always rises, right? And we're supposed to be able to count on it's the total number of minutes since the object was created, and suddenly that's violated. It doesn't cut it. Well, okay, so this is related to the previous one. Okay, how about this one? Here's a read-only int set, and here's a derived int set that also, it extends read-only int set, but it also has a thing called size. It returns the size of the int set, the number of things in the int set. Is that a legitimate subtype? Yeah, it's fine. It's fine. Our code knows only that it's maybe the code that's using only the read-only int set knows that that it's read-only int set. It doesn't know about the size method. It's treating it perfectly fine. Somewhere else in the code, maybe the place that created it, knowing that it's a derived int set, maybe some other code that It also knows it's a derived inset. Maybe it's calling size all the time, but it doesn't interfere at all with the correct operation of this code. People comfortable with that? Okay. How about this one? Derived inset 2. This one inserts something in there. So we make all use of all this functionality implementing and read-only inset, but we also want to add a little bit more functionality. We also want to insert things into that set. Is that legitimate?
No,
Why not? Good.
because it's allowed to modify it's not read only.
It's not read-only anymore. Someone may be counting on the fact that, hey, if it isn't there up front, it gets created, passed to us, and we say, hey, is this thing in there? And the answer comes back, no. We know then from now on, that thing is not in there. There's no, 3 in this set. We checked it once, and we know we don't have to check it again, right? There's no way, if it wasn't there early on, no way that's changing, right? With the read-only inset. Suddenly, if we have this way, somewhere else in the code, you can go insert this thing. You can go insert 3 in there. We may have checked early on, oh, 3's not there. 3, you could use that as a free value of the array. It's an unallocated slot or whatever. Suddenly, somewhere else in the code is called this insert, and again, it's modified this thing we know only as a read-only inset, and suddenly the thing we're counting on is in. We've been counting on it being false for the argument 3, and suddenly, boom, it's actually true. Bad news. Do you understand that? Okay, good. Okay, how about this? This may be our final one here. Maybe another. Okay, so here's a read-only dictionary, and here's my read insert dictionary that inserts elements in here. It inserts elements into this thing. Is this a legitimate subtype? No, for the same reason. We're counting on it being read-only, counting on it being immutable, and suddenly we've made it mutable, and it could break the fact that we before are counting, we checked once, and we don't have to check again. Whether a certain thing is occupied, and suddenly now the value of this can change over time with respect to this value passed into us. Somewhere else in the code that knows it's a read insert dictionary calls this thing on a thing that we think is merely a read-only dictionary, and suddenly our assumption that you only have to call this once and you can count on its value, suddenly that assumption is out the window. Okay, here's a slightly subtle one. How about read insert dictionary? Suppose that's a supertype. And then we have a read write dictionary that can actually update elements. So here we can only insert elements. Here we can actually update. So we can insert elements into this dictionary. So we can insert new strings that weren't there before with some value. Here we can actually update the values associated with strings that are there before. Is that a legitimate subtype? No. Because someone could have checked the value once and say, well, okay, it's in there. It has the value 3.141592625, and they know they don't have to check it again. And suddenly now it can be updated, and we might have to check it again. And so it could be bad news. Okay, so those are some examples of the Liskov substitution principle as applied to particular cases. And I hope that you'll come away with a few high-level points. First of all, it's not easy. Second of all, and it requires thought. Second of all, this is not about putting us in a straitjacket. This is not about you can't add significant functionality. You can't. You just can't add functionality to a class for subtyping that breaks the thing someone could be counting on for the super. And if you're going to create a supertype, folks, if you're going to create a class which can be subtyped by somebody, if you're going to leave that open to them, for example, by not declaring it a final class, then you might want to put in some things there that are very explicit about what you can count on and what you can't. We call them specifications. We put those for methods. This method behaves in this way. You might even put things in there. It's Matthew asked about, I think, last time. You might put things in there related to his question. For example, let's say, note this value is always non-negative. Or, do not count on this value being non-negative, because this might be modified legitimately by subtypes. We could actually state that. If we don't want people to be counting on these things, if we want to allow flexibility for subtyping, we might want to say, hey, don't count on this. But ladies and gentlemen, the Liskov substitution principle, and this is one of the key points I want to communicate, is all about promises. It's about what could we be counting on? What could be thinking is guaranteed from the supertype? Next time, ladies and gentlemen, next class, we're going to be looking beyond the issue of promises. Maintaining these promises is key to avoid bugs. It's key to avoid in the Liskov substitution principle. That's why we're talking about it. It's key to avoid breaking code, particularly code written by other people who knew only, they didn't know about your class, they knew only about the supertype. Next time, we will be talking further about subclassing and inheritance, which brings its own set of additional worries, additional concerns, additional care that's needed. And where, guess what, folks? You're not just worrying about the promises made, but you're worrying about the implementation of the superclass. Now it's not merely you have a super type. You're actually inheriting the implementation of you're inheriting how it works, all the pieces of that superclass. And now you're going to have extra responsibilities associated with that, incumbent upon you become that. And you're going to need to know about something about how that superclass actually works, how it's implemented, not merely about its promises offered to all users, to all clients of instances of it, but you're going to have to worry about actually how it's implemented behind the scenes, what method calls what method, for example. And we will see that next time. And it's of direct relevance because if you're creating classes that are going to get subclassed, you'll want to have some documentation about what things call what other things, for example, just like the Java standard libraries do for this reason. Okay, so we're going to see that next time. Good luck with your ID4s. I'll look forward to reviewing them. Again, I was very impressed with the team's work in refactoring code, and I'll look forward to reviewing some code from the other team as well as further ones from that code base after your hand-in Saturday night. I know you're working really hard in a lot of classes, and I want to tell you I'm pretty impressed with where you are. Keep up the good work, and I think we'll come in for a soft landing in both teams. Okay? Very good.